thank you for coming. My name is Lorenzo Trojan. I work for a company called Axial 3D, and we work within the health sector. We have a very interesting application, and today I'm here essentially to talk about what we do. Now, the reason why I've decided to come here and I decided to ask to give you this talk is because it's a very cool application, and we do use Python. But it's in the healthcare, like I said, and I come from a different background. I'm actually a physicist, and when I joined this company, it was great. It was very refreshing because I was working on something that it does give you the feeling of helping people. It does give you the feeling of doing something that is good. It cures patients, and you do use very cool technologies. Now we do use Python, like I said, and that's the primary language that we use for all the sort of researchy and image processing pipeline, which I'm going to be talking about in a minute. And the reason why we use Python is essentially because it's great. It's a great tool. And like I said, I'm a scientist to start with. And as a scientist, one of the greatest things is that with Python, you are empowered, like we heard before, of writing an algorithm just exactly like you want to write it, and then send it to production almost immediately. It's almost ready for production, and that's great. It gives you a great, refreshing sort of feeling to it. I come from a world where you used to write in MATLAB maybe, a little algorithm. You would use vectorized notation to speed up the development of the algorithm. But then a software engineer would have to take that code and turn it into something that can actually be running on the cloud maybe, on microservice of some kind, and that's difficult. If you're a scientist, you don't want to do that. You just want to write your code. You just want to focus on the algorithms. And this company has given me that chance, which is great. And there's another thing as well. I'm a bit of a Python enthusiast myself, and we heard yesterday a talk about how cool it is to write code, right? There was what was it? Oh, bloody hell. Miguel, who's given us a talk about how cool it is to write Python code, and Python code in particular. And I feel the same. I feel great. I can do in my job what I like to do, and that's a fantastic place to be. So now let's start with about the problem that we are dealing with. Now, what we work with is what you could be calling three-dimensional scans of patients, right? So, and I'm talking about CTs and MRIs in particular. And why are they useful? Because they give to the clinicians an insight of the patients, how the organs are arranged within the body and what the condition looks like, its volume, its shapes, and the surgeon, in this case, can prepare exactly how he wants to do the operations once he knows exactly how the lesion is going to look like. The radiotherapist is a person who cures tumors. Many people, when they have a tumor, they will be sent to radiotherapy. There's going to be a clinical person who will assess the size and shape of the tumor and decide exactly how to irradiate the patient in order to kill as many nasty cells of the tumor and as little good cells of the body, of the healthy tissues. And in order to do that, the radiotherapist needs to know exactly where the tumor is located, exactly its shape, the metastasis, if there are metastases, etc., etc. Another scenario is the orthopedics surgeon or orthopedic medical doctor, who again will have to know exactly how a ligament is broken, in what way a ligament is broken, in what way a bone is broken, in order to decide how to cure the patient. Now, a patient may have to go through surgery, so we'll go back to the first person in this little slide, or he may decide to put the patient in a cast. And depending on the type, the severity of the lesion, the orthopedic has to make a decision about what to do next. And there's not just these three, there's a wealth of other doctors who need three-dimensional scans in order to make decisions as to how to cure patients. I put here a cardiologist, and that's the little heart, and a neurosurgeon who again will operate on patients which have conditions within the head, inside the skull sometimes. So they could be tumors again, they could be something called an aneurysm, which is essentially a vessel that has lost its integrity and has expanded beyond its correct shape, and therefore it pushes it creates pressures within the skull. And very often these lesions have to be operated on, so they will have to essentially cut the skull, open it, and go inside the skull with some tools to remove these lesions or these conditions. And so what do they have all in common? They need to know the size and shape of the lesions or the conditions. And to do that, we developed a very cool technology which is called computer tomography. This is a little video that I always show in this kind of situation because I think it's terrifying. That's a CT in operation. Now, normally a patient won't see this because all that big gantry is covered by a sheet of metal, so you don't actually see it. You just hear the humming, and that's what's going on. As you can see, there's a little piece of tissue that is flying around because of the wind. I'll skip a little bit in the middle because it gets more interesting. Now, the patient is here, right? I would be completely terrified of going inside one of these machines, which weighs a couple of tons, and they spray me with x-rays. Not nice. However, it's great because you get these nice scans on the side. Now, I'm not sure whether you can see this, but there's actually already a problem, and you can already see that problem in this scan that you see on the right. That's obviously a hand, and it's a CT that goes from about just before the wrist to about halfway through the arm. And what's the biggest problem? The biggest problem is that if you didn't have the graph to the right, when you're looking at those images, you wouldn't know where the image is exactly located. And this is just my own rendering. I just created that graph for the purpose of this demonstration, but normally that's not how a doctor will visualize this data. And there will be another little slide later, but oops. That's another very cool technology. It's called MRI or MR imaging or magnetic resonance imaging. It produces something very similar. This is not a movie, but it could have been a movie. There's a slight difference in the way the patient is seen through the NMR scanner. In a CT scanner, very thick tissues will appear dark, and very thin tissues will appear very bright. Whereas in an NMR scan, what's bright is tissues containing a lot of water. So depending on the water content of your tissues, the scan will be darker or brighter, which makes bones look very dark. I don't know, there's a band here. You cannot even see it really. I think it's there. That's the skull. And then the water content in the brain is a lot higher, and therefore you see these patches of grey. And apparently there's a lot of water in the mouth as well, etc., etc. That's the machine. It's not as terrifying. I did have a video of showing how this machine can be dangerous, but I'm not going to show it to you. But just to give you an idea, I think it was an engineer wanted to fix the machine and went with a screwdriver, and the machine was not turned off, and the screwdriver flew across the room, and if there was a person in the middle, I'm not sure what would have happened to that person. But anyway, like I said before, what's the biggest problem with these images is that that's how they are seen today by clinical doctors. You essentially sit in front of the monitor and you're trying to go through those images one by one, and sometimes you get a nice little rendering here. I don't know whether you can see that in three-dimensional, but it's still a two-dimensional image shown to you through a screen. So it doesn't really, a person like this, let's imagine this is I'm not entirely sure what this doctor is, but let's say it's a surgeon. Surgeons, they're very manual people, right? They touch things, they touch patients, they want to go with their hands and see what the problem is, right? And they're not software developers, they don't like a monitor, they only use it because they have to, but they would be perfectly happy to get rid of their monitor if they could. So that's the biggest problem that we try to address here in Axial 3D. And there's not just us, there's a lot of people. But in the last, I'd say 5-10 years maybe, one of the ways that we can help the doctors make the decision about what they should do with a specific patient is through something like this. So these are 3D printed models. They are extracted from the CT scans. These are all these three are CT scans. What you can see here is a spine of a scoliotic patient. This is a foot. The red material here was an implant, a metallic implant. And I believe this is a tumor in the arm, and the little red patch here that developed inside the bone. These are actually Axial 3D models, and what we found is that we've been talking to a lot of surgeons, and we do try to spend as much time as possible to build a product, obviously, as they want it. One of the things, though, is that we found some. What you could be thinking is, why do you not use VR technology? That's another option, right? You could be creating, rather than printing them, you could just create a VR system, maybe like a VR cave where the surgeon can go in and actually experience the same thing without using 3D printing technology. Well, there's a lot of doctors and there's a lot of associations that have basically released a number of reports where they point to the fact that VR is one of the very cool technologies, but doctors just like to hold one of these in their hands. They just like to touch it. They see it, and another very cool thing is that they can show it to the patients. So they can go to the patient and say, well, look, this is exactly how your bones look like. There's not just bones. This is not one of. This is a research team. They did this very cool, interesting experiment. So I'm referring to these images here. There's a procedure that's been. They started doing it, I think 5-7 years ago, maybe, which is called TAVI. And this procedure, it's a cardiac sort of procedure. In elderly patients, sometimes the valves in the heart stop working properly. They don't shut properly. So what happens is that because they don't shut, the heart muscle doesn't manage to create enough pressure to pump the blood through the body, so you can imagine this pumping thing, but doesn't manage to pump enough blood. Now the patient gets really tired; he can't do anything anymore. He cannot even stand up from the bed without feeling totally tired, and it generally affects all patients. And the fix for this is to implant a new valve. So we can build valves and we can implant in the heart. But what the problem is that to implant something on the heart requires heart surgery. Heart surgery means that you open up the sternum, you have a specific tool to split up the entire chest, and you expose the heart. It's a terrifying operation, if you can imagine that. And you cannot put an older patient, 70 years old patient, through this. It's an ordeal, and you don't want to put such an old elderly patient through this operation. So what you do is you try to give some kind of medications to mitigate this issue. You can only do it on young patients. With the TAVI, what they do is, rather than opening the chest, they make a small incision in the leg. They insert a little wire inside the veins. The wire follows the vein, get all the way to the heart, and once it gets to the heart, just in proximity of the aortic valve, it opens up and the valve replacement comes out of this wire and gets placed in the correct place. Now that allows this type of operation to be carried out on an elderly patient, and it's great, it's fantastic. There's one problem though, and the problem is that the clinician will not be able to see what's happening. The only way the clinician can see what's happening is through an X-ray, which is very fuzzy. You can see this little metallic wire going through the heart, going through the aorta, reaching the heart, and you think, yeah, it's about there, and you'll open it up. But what if you could do a 3D printed model of the entire aortic arch and try out the operation, and maybe even put this 3D printed model in an X-ray scanner and actually see almost exactly how it would look like when you do it on a real patient. I put here another two examples of 3D printing technology applied in the healthcare. I'm not going to go into the details because otherwise it would be too long. This is another case. This is again another Axial 3D case. There's many more. I'm only showing these three. That's a kidney, and this is the operation. So that's a real kidney from an elderly patient which had a lesion and had to be implanted on a younger patient. Now there was a little lesion inside this kidney that had to be removed, and this is a 3D printed model. You can see better here. That black blob is the lesion, and this is our main investor showing this model, this 3D printed model, to this person who I'm not going to name. I am going to. Arlene Foster, the Prime Minister, ex-Prime Minister of Northern Ireland. Okay, what's the problem though? This is a great story, right? 3D printed model helps surgeons improve lives. Great. What's the problem? Well, the problem is that before you can build one of those 3D printed models, you need to perform segmentation on these images. Now, this image doesn't look particularly bad, but for one of those scans that I was showing earlier, there could be 500, 700 images, right? And to perform a manual segmentation on these images could take easily 4 or 5 days of a person or a radiologist. A radiologist who is a very highly trained, skilled person who's extremely busy doing radiography of patients. You don't want to put a radiologist just spending hours and hours and hours for one single patient because you want to build a 3D printed model. So what you do? Well, this is another example. Just to give you an idea. Let's see. That's a pelvis, a shattered pelvis. And this is one of our cases. We did this manually ourselves. It took about, I think, again, 4 hours. The blue is the segmentation that was selected manually by one of our engineers. And that's the 3D printed model that you extract from the manual segmentation. That's another little movie. That's a skull. Now this takes a lot longer. I don't exactly know how long it took to produce the segmentation for this. But if you can, this is not working. Okay, I'll skip it. But it takes a lot longer, depending on the condition, depending on what kind of body part you're trying to segment. It could take longer or shorter time, but no less than 2 or 3 hours. Now, one of the solutions is, let's use machine learning. Let's use deep learning in particular. Deep learning is a new technology, as you probably heard hundreds and hundreds of times. It's fantastic. Since 2013, which is about here in this graph, it's been shown to outperform pretty much any algorithms in the image processing domain. And it's fantastic. It's been applied to hundreds and hundreds of different applications, self-driving cars, VR, healthcare. And the quality of the results that you can get from these type of algorithms is testified by these graphs. So this is the number of publications in PubMed in the last 60 years, right? Image processing, mentioned a lot of times, it already started in the 80s, and then it kind of plateaued in the 2000s. In the 2000s, we start seeing a lot of publications mentioning machine learning as one of the keywords, and since 2013, deep learning has this massive, this is a logarithmic scale, by the way, so these are actually very high numbers. And apparently this is the first year that machine learning is overtaking image processing in the number of publications. Great. And possibly next year, deep learning will overtake both image processing. Who knows? We'll wait for next year to know. But it's incredible, and it testifies how good these kinds of technologies can be. And this is just an overview. I'm sure you've probably seen a lot of these logos. This is a software development conference, so I have to have a slide like this one. The great thing is that in the last year, and what I want to say with this slide is that in the last 5 years, probably 4 or 5 years, there's so many tools there, and it's incredible. And I'm going to get back in the next slide as well about this. And as a scientist, it's fantastic to see all these tools, because I don't know if you ever used one of these. SageMaker uses Jupyter notebooks, which you've probably heard hundreds of times already in the last 2 days. You go on, you create your online machine that runs a Jupyter book, and you can try straight away in just a matter of minutes an algorithm, and that's fantastic. That's the Google equivalent. Docker, obviously everything runs on Docker. NVIDIA is since the mid-noughties has put a lot of investment into machine learning, so I mentioned them as well in here. And this is the wealth of, there was a very similar slide just a minute ago. That's just some of the packages that you can use. I've added, compared to the slide that we saw about half an hour ago, I added these three, which are much more deep learning oriented. So one of them is Keras, the other one is TensorFlow, and this one here, which I don't particularly like to talk about, is PyTorch. And what can you do with them? Something like this. This is the original AlexNet, which was developed in 2013, and this is the algorithm that actually made a massive breakthrough. And since that algorithm was published, we have, since that algorithm, we really have seen how deep learning can be applied to machine learning applications and image processing applications. This is a little idea of what these blocks are supposed to represent. These blocks are made of, the first block is made of simple features, and let's say the following block, or maybe this block here, will combine this simpler feature into make more complex shapes. And you can make more and more and more and more complex shape until you get at the end, and hopefully you end up with something that says, in this image there's a dog, and in this image there's a cat. One of the problems with this kind of technology that we have in Axial 3D and a lot of other people have is that this specific implementation tells you what's in the image, but not necessarily what's where within the image that a specific object is found. So in 2013, 15 maybe, a group of Germans came up with this sort of cool architecture. The first bit here is exactly the same as AlexNet, but in here, instead of just stopping there, you can use the labels, and you can somehow combine them with the previous features to work out where those labels are located. And you can work it back up until the original shape of the original dimension of your image. Great, so that's exactly what we are after. This is essentially a segmentation algorithm now, not just a labeling algorithm. Oh, now I've got a little demo. Let's see if I can move it across. Now, the cool thing about this is that this is running on a Google Cloud platform. So like I said before, it's fantastic. And as a scientist, you don't need to worry too much about DevOps, right? Which is another thing that we heard just a few minutes ago. You don't need to worry too much about that. All you need to do is just say to somebody, can you give me a machine? Well, there's somebody's actually a website, but can you give me a machine with a GPU? And there you go, there's your GPU-enabled machine. Or can you give me the GPU with also all the packages that I need to run my machine learning application? Yeah, there you go, here it is. And in literally like 2 minutes, you have your machine with a Jupyter notebook that is running, and you can start experimenting. So let's see if I can run this. Hopefully it's actually running. Yeah. Okay, so a little bit of explanation here. I don't need to go too much into the details. We heard about this already during this couple of days. One of the big problems with data scientists and image processing community and building these algorithms is you need a lot of images, and you need to sort them out correctly. So here there's a little bit of details about how I've sorted my images in this specific case. I set them into a train set and the train set and into a test set. I have a subdirectory with all the images and a subdirectory with all the labels. And the same for the test set. And let's see if I can run it. Can I run it like this? Yeah. And this is how my images kind of look like. They are CT scans, like I mentioned earlier, and this is the ground truth. So that's highlighting the bones again. Oh, actually, that was okay. We don't need to get into this. This is just a little bit of functionalities to load the images in the correct order and sort them out so that you have one image and the correct labels for each image. Have I run it? Yeah. And and this is just a little bit of functionality to sort out the images so that they look correct. So the idea here is that the labels have to be either 0, 1. So 0 if it's not a bone, 1 if it's a bone. So I'm turning that into a Boolean array. I'm assuming that you have at least heard about NumPy because you heard about it 10 minutes ago. So I'm just going to skip what all this. Another thing that I wanted to mention, and I forgot, another cool thing about NumPy is that if you're used to mathematical notation, the vectorized form is just exactly the same as a mathematical notation. So when you're broadcasting, it's exactly the same that you would do in mathematics on a piece of paper, right? You have a vector plus 1, and you write it exactly in the same way in NumPy. So here, this is a 3-dimensional array. I can just check whether it's greater than 0.5, and that will turn my array into, well, it will return a Boolean matrix of the same shape with each element, whether it's greater or not, compared to 5. Here I'm casting it to float because I want my images are read in as 8-bit integers, so I need to have them in floating point values, and I want to normalize them to 255, which is the highest number that you can get in unsigned integer. So that's turning my images from images that vary between 0 and 255 to 0 to 1 in floating point. And let's run this cell, and let's run this cell as well. This will take a little bit longer because it's actually loading about, I think, a couple of 1,000 images. Oh no, have I got? Oh, haha. I don't need test. There you go. I knew there was going to be a problem. What did I call it? Train. And train. So now I'm printing here the shape, which will give me an indication of how big my data set is. And well, here we are. So the shape in the train test, in the train set, there's 1,237 images. Not bad, but not nearly as big as what you would need to create a proper algorithm that goes in production. But it's good enough for this demonstration. It's quite substantial actually. You don't often see medical data in this sort of volume, so that's already a good thing. And this is how it looks like. That's just very similar to what we had before. And this is the key thing. That's the coolest part. That's how we create in Keras, which is one of those libraries to run machine learning, deep learning algorithms. We're using Keras here to create a model that is called a sequential model. So we are stacking, like I had shown you earlier, we are stacking a set of convolutional filters. And we are specifying what each one of those convolutional filter, the shape, which means how many filters I want in each one of these filters. If I go back, that's equivalent to say how many lines I want in the first layer and how many potential features I want in the following layers. So how complex your features can be or not be. And in here, this is just a utility function. It takes how many channels your input images have. So in our case, it's only one channel. It's grayscale images. How many classes you want to predict. So in our case, it's only one class. It's either bone or not bone. And a list of layers, which is just how many convolutional filters you want. Each one of these convolutional filters is going to be 3 by 3. So we've got 3 small patches of convolutional filters that go over my image and try to identify specific features. And I stack them into this very small for loop. Sorry, there is a for loop. I hope you're not going to hate me for that. But it runs, and not entirely sure why I've got this block here. I probably was thinking about doing something extremely clever, but and here we build my model with this function that I just shown you, and I'm creating a model which has an input layer, only a grayscale image, an output layer, again only a grayscale image, where ones will represent bones, 0 represent not bone. In the first layer, I got 16 of those little squares, and then 32 more complex features, and then 64, 128, 128, 128. So there's 1, 2, 3, 4, 5, 6 filters. The nice thing is that I could actually remove this and try a simpler architecture. Okay, I could carry on with more filters. I'm not going to do that because otherwise the training would take forever. 28. So let's build my model, and this is how easy it is to actually build it. So let's see. So what I always do is we compile the model, and compiling is a step required, at least in Keras, to allow the model to understand how it's meant to learn the features. In this specific example, we are using something called SGD, which stands for stochastic gradient descent. Gradient descent is an optimization algorithm, and it just tells how the algorithm is supposed to learn those little features. And the learning rate, the momentum, we don't need to go into that. And the metrics is just telling the model that every step, every time it's learning something, I want to use the accuracy measure to see how well my model is learning. And then we fit the model. So we pass the images and the labels, which I loaded previously. And I want to go over these images 6 times, all of them. So it was 1,200, about 1,200. And I cannot go through those images all at once, so I'll go into groups of 10 images at a time, and I'm going to use part of these images to actually validate, so to actually measure how well my model is performing. And let's see how long this is going to take. It should be about 6 minutes. So in the meantime, I'll go through a little bit more. This is another architecture for these neural networks. I'm not going to describe it in details.
but it allows these networks to be a lot deeper. So thanks to this this is called a skip connection, and it allows my network to double, treble in size, or even 20 times as big without incurring problems training this network. That's what I mentioned earlier. And this is a nice slide. I mean, these are just the collaboration that my specific company has currently going on with other institutions. But what I want to say with this is that one of the key things for machine learning, deep learning, is that you, in order to be successful, you need to talk to as many people as possible. So these are just 3 architecture. There's hundreds of them, and there's hundreds and hundreds of people trying to experiment, try different approaches, try different small parameters. These networks can be configured in hundreds and hundreds and millions of different ways, and you can build them, stack them, change them, put 3 or 4 networks in parallel and try to do, you get one network to do one thing, another network to do another thing. There's hundreds of people out there, and the more you talk, the more successful you're going to be. So this is very important. And if you are thinking about moving into machine learning and deep learning, consider to talk not just to academics, but to industry as well. There's a lot of very, very good engineers. They are doing very cool work, and they like to go to conferences as well. So go and talk to them. I just put it also, that's Meetup. And Beltec, Belfast, yeah. And obviously Stack Overflow. Thank you, Stack Overflow. That's the best place to find information about almost anything you want. And this is a very quick slide about us. This is our senior team, Daniel, Niall, Katie and Kathy. And this is just a summary. Again, I don't want to just say how cool we are, but it's really about talking to people. You're not going to be very successful in machine learning, I don't think, personally. Again, I'm talking as a scientist, and I don't think you can be really successful if you don't talk to people, and you don't go to conferences, and you don't talk to PhD students and master students, etc., etc. And there's a little note here in case anybody is interested. But this is still going. What a shame. So I'm not going to. I've already created these plots, so I'm just going to show them to you. I'm not going to run them. Once you've finished your training, you can actually see this is a plot of the accuracy of the model as it's training. So this is currently training. This was trained on only 200 images. I tried it last night, and as you can see, sorry, it's not the accuracy, it's the loss. The loss is a measure of how bad it's performing, so it's not the accuracy, it's how bad it is. And that's what's actually being used to learn. And as you can see, it's still at the very beginning of the learning, so I just wanted to make sure that it was working. In principle, this number here is supposed to go to very close to 0, so 10 to the minus 2, 10 to the minus 3, or something like that. This was another little bit. This is an evaluation of the quality of the results that we can get exactly from the network that was running now, that's training now, on the test set. Oh. Was this updating?
No, it's just kicking the ball.
I was just moving, yeah, right. And it's just a histogram of how well it performed over new images, the algorithm, so the segmentation algorithm. And as you can see here, that's the accuracy now. The accuracy is between 2 and 4%. Sorry, no, it must be the loss. Between 2 and 4%, so it's very accurate. So let's say 98% accurate. And this where, I don't know how many images about, was it 200 in the test set? I think about 200. No, that can't be, because otherwise it would have been more than 7, but never mind. And that's a little, and that's just an example. That's the input image, and that's the segmentation. That again, it was the one I trained 2 or 3 days ago, I think. Which is still here, this graph. So as you can see, it's not 100% perfect, because that's not bone. That's actually a little support that was holding the head in place when they did the CT scan. And it's been picked up as bone, unfortunately. It's a bit yellow. But otherwise, it's pretty good. It's actually not seen, it's not picked anything within the skull, which is great. So I hope you enjoyed. That's it, pretty much. I didn't put my number. In case you have any question, I'm here. You can ask me now, or you can ask me later. I hope you enjoyed.